Every day, we rely on probability to predict the weather, to time our commute, to decide whether to carry an umbrella. But if someone asked you what probability actually is, could you give a precise answer? Most people would say it's a measure of how likely something is to happen. That's true, but it's also vague. Today, we're going to build a rigorous definition from the ground up, and we'll discover a surprising twist. Probability, at its core, is a volume. Not a physical volume, but a mathematical one. By the end you'll see how a simple idea, measuring the size of a set, unlocks the entire foundation of probability theory. Let's start with the basics. What does it mean to quantify randomness? Probability is our attempt to assign numbers to randomness. But here's a subtle point: mathematics doesn't actually define what randomness is. It could be that events are truly random, or that they're determined by hidden factors we don't yet understand. Mathematicians sidestep this debate entirely. Their concept of probability works in both scenarios. We interpret probability as a degree of confidence that a particular event will occur. And we measure that confidence on a scale from 0 to 100%. 0 means it will never happen, 100 means it's certain. But to build a rigorous framework, we need to move beyond percentages and think in terms of functions and sets. That's where the real power lies. Let's formalize this. We want a function that takes an event and returns a number between 0 and 1, representing its probability. This function is called a probability measure. But to define it properly, we first need to specify what an event is. In probability theory, we start with a sample space, often denoted by the Greek letter omega. This is the set of all possible outcomes of a random experiment. An event is simply a subset of that sample space. For example, when rolling a die, the sample space is the set 1, 2, 3, 4, 5, 6. The event rolling an even number is the subset 2, 4, 6. So our probability measure takes a subset, measures it in some way, and returns a number. The question is, how do we measure a set? It's easy to confuse outcomes with events, but they're distinct concepts. An outcome is a single possible result of an experiment. An event is a set of outcomes that we're interested in. For instance, when rolling a die, rolling a 4 is an outcome, while rolling an odd number is an event that includes the outcomes 1, 3, and 5. Events can be simple, containing just one outcome, or compound, containing multiple. This distinction is crucial because a probability measure assigns probabilities to events, not to individual outcomes directly. In fact, in continuous spaces, individual outcomes often have probability 0, as we'll see later. To define a probability measure, we need to specify which events we can measure. This collection of events is called an event space, or a sigma algebra. For a finite sample space like a die, the event space is simply the power set, the set of all subsets. That includes all possible combinations of outcomes, from the empty set to the whole sample space. The empty set represents the impossible event, and the sample space itself represents the certain event. This structure ensures that we can assign probabilities to any event we might care about, from rolling a 4 to rolling a number less than 5 and even. Now we come to the heart of measure theory. A measure is a function that assigns a non-negative number to sets, representing their size or volume. For a probability measure, we add 3 specific rules. First, the measure of the empty set must be 0, nothing has 0 volume. Second, the measure must be non-negative, we can't have negative probabilities. Third, the measure of a countable union of disjoint sets must equal the sum of their individual measures. This is called countable additivity. These rules might seem abstract, but they align perfectly with our intuition about volume. If you have 2 non-overlapping shapes, the total volume is the sum of their volumes. Let's apply these rules to our die example. We have 6 outcomes, each equally likely due to symmetry. So each outcome gets a probability of 1/6. The empty set, rolling a 7, for instance, gets probability 0. The entire sample space, rolling any number from 1 to 6, gets probability 1. And if we want the probability of rolling a 1 or a 2, we simply add the individual probabilities. 1/6 plus 1/6 equals 1/3. This works because the events are disjoint. This simple example illustrates all three rules in action. But what if the outcomes aren't equally likely? That's where we need a more flexible tool. For discrete sample spaces, we can assign probabilities to individual outcomes using a probability mass function, or PMF. The PMF, often denoted by lowercase p, maps each outcome to its probability. For a fair die, p1 equals 1/6, p2 equals 1/6, and so on. The sum of all PMF values must equal 1. The probability of any event is then the sum of the PMF values for the outcomes in that event. This is analogous to adding up the lengths of segments representing each outcome. The PMF is a different function from the probability measure p, but it's a convenient way to specify probabilities for discrete spaces. Now let's move to a continuous sample space. Imagine waiting time in traffic. The possible waiting times are all real numbers from 0 to, say, 6 minutes. There are infinitely many possible outcomes, and they're uncountable. In this case, assigning probability to each individual outcome is problematic. If we try to assign a positive probability to each, the total would be infinite. Instead, we need a different approach. We'll use the concept of area under a curve, which leads us to the probability density function. This transition is the key to understanding continuous probability. For continuous spaces, we use a probability density function, or PDF, denoted by lowercase p as well. The PDF is a non-negative function, but its values are not probabilities. Instead, the probability of an event is the area under the PDF curve over that event's interval. For example, the probability of waiting between 2 and 3 minutes is the integral of the PDF from 2 to 3. The total area under the entire PDF must equal 1. And the probability of waiting exactly 2 minutes is the area of a line, which is 0. This is why individual points have 0 probability in continuous distributions. Why do we call probability a volume? Because measuring a set's probability is exactly like measuring its size. In one dimension, we measure length. In 2 dimensions, we measure area. In 3 dimensions, we measure volume. A probability measure assigns a volume to each event, whether it's a subset of the real line or a higher dimensional space. For discrete spaces, we can think of each outcome as a segment with length equal to its probability. For continuous spaces, we think of the area under the PDF curve. This unifying perspective is what makes measure theory so powerful. Let's compare the probability mass function and the probability density function. The PMF is used for discrete random variables, where outcomes are countable. It gives the probability of each outcome directly, and the sum of all probabilities is 1. The PDF is used for continuous random variables, where outcomes are uncountable. It gives a density, not a probability, and the probability of an interval is the area under the curve. The values of a PDF can be greater than 1, as long as the total area is 1. Understanding this distinction is crucial for working with different types of random experiments. What about experiments with infinitely many outcomes, like the number of planets with life? Here, we can't rely on symmetry. We need to assign weights that sum to 1, even though there are infinitely many. This is possible if the weights decrease fast enough. For example, a geometric distribution assigns probabilities that decay exponentially, and their sum converges to 1. Similarly, for continuous distributions, the PDF must have a finite integral. This is a fundamental requirement. The total probability must always be 1, no matter how many outcomes there are. So, we've seen that probability is not just a vague notion of likelihood. It's a rigorous mathematical concept rooted in measure theory. A probability measure assigns a volume to each event in a sample space, following 3 simple rules. For discrete spaces, we use probability mass functions. For continuous spaces, we use probability density functions. The volume analogy unifies these ideas. Whether we're measuring lengths, areas, or higher dimensional volumes, the underlying principle is the same. This perspective not only clarifies what probability is but also provides a powerful tool for tackling complex problems in science, finance, and beyond. Stay curious. Markets reward discipline, not certainty. If this analysis helped, like the video and subscribe to DeepQuant. Tell us in the comments which market idea we should test next. Evidence beats noise. Control risk before chasing returns.